Welcome back, everyone. So, like all good things, everything needs to come to an end. This time, this is this year's BalCCon. Our last talk, but definitely not least, is titled Where is my cache? Architectural patterns for caching microservices by example. Please welcome Rafal Leszko.
Hello, I'm Rafał. I came from Poland. I arrived actually today. I must tell you that this BalCCon conference is super unique. I've never seen before like self-made TV out of LEDs. It's really impressive, and all the things. I'm really happy to be here. Thanks for coming for this talk. So today I will tell you about caching, especially caching in the microservice world, in the microservice architecture. But first, a few words about myself. So I'm a cloud software engineer at Hazelcast. Before Hazelcast, I worked at Google and CERN. I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from the time to time, I do conference speaking and trainings. A few words about Hazelcast. Hazelcast is a distributed company. It's distributed in two meanings. First is distributed because we produce distributed software. And the second is distributed because all members work remotely. So we have people from all over the world. Our products, we produce open source software. So you can use everything. Everything is on GitHub. We have three products. The first product is the most known, is Hazelcast IMDG, which is kind of a caching solution. We call it caching on steroids because it actually has a lot of features other than caching. The second product is Hazelcast Jet. It is a library for big data stream processing. And the third one is Hazelcast Cloud. So it is a cloud solution for Hazelcast. So cache as a service. Our agenda for today is pretty simple. So there will be a very short introduction about caching in general. And then we will walk through all the patterns that you can use in your system. I would like you to answer two questions while watching to this presentation. First is, what cache do you use in your company, in your environment? You definitely use caching, so you must use one of these patterns because this list is complete. And the second question is, I would like you to ask yourself is, can I change to any other patterns? If in my software architecture, does it make sense to change it? So let's begin. Why caching? So everybody does caching, and no matter what software you write, no matter like which programming language, and we do it for two main reasons. One is the most obvious, is the performance. So instead of doing some business logic, some long-time processing, we just cache some value and then return the cached response. The second one is a little less obvious, is about resilience. So it means that even if our system is down, we can still return, sometimes we can still return the cached value to the user. And the user may not even realize that our service is down. For example, if you imagine that you work in Amazon and you implement the Amazon recommendations. There could be easily cached, and even if the Amazon recommendation service is down, you can return a cached value because it's not critical to the business. So you can use caching for improving your resilience to failures. Now, what to do with the microservice architecture? In the microservice world, this diagram is a sample microservice architecture. You have many services. They can be written in different programming language. They use each other. They have versions. So now the question is, where is the right place to put your cache? Is the right place to put it inside your services? Or maybe as a separate unit, as a cache server, or maybe in front of each service. And that is what this talk is about, because there is no one good solution to these questions. So let's walk through the possibilities you have. So the first one, the simplest possible cache, is embedded cache. It works as follows. A request comes to our system, it goes to the load balancer, then the load balancer forwards the request to one of the application web services, and the application receives the request, it checks in the cache if the value for some operation, and then if there is no cached value, then perform some business logic. If no, then if the value is in the cache, then return the cached value. That business logic is whatever. It can be long time calculation, it can be call to external service. For sure, it's something that takes a lot of time. So it can be also a call to the database. So something that is worth caching. That is inside our application and runs together with our application. So we can even think about writing the code ourselves for this. If you happen to use Java, like that would be the very simple code to implement our cache ourselves. So we could use concurrent hash map, and that is exactly the algorithm. So the request comes to our service. We check if the cache contains the request. If yes, return the cached value. If no, do some processing, put the result into the cache, and then return the result. So you can implement it yourself. However, don't do it, because such a simple implementation based on the standard library is not actually a cache. It's not a cache because it has no eviction policy, no max size limit, no statistic, no billion cache loaders, no expiration time, and no notification mechanism. So it is not really a cache. Way better solution is to use some library. If you happen to use Java, then you can use Guava. It has all these features built in, which you can set up at the beginning of the creating of the cache. The other solution is EHCache, which is also a very, very good solution. If you don't want to implement all this caching logic yourself, we can move the caching one level higher to the application level. For example, in case of Spring, it's enough to add a few annotations, and the cache is automatically used. So in this example, we just added the annotation cacheable, and now every call to our method first checks if the given ISBN is already in cache. If yes, return the cached value. If not, perform a process with the method find, book, and slow source. However, be careful, because Spring by default uses concurrent hash map. I don't know why, but they did it that way. So coming back to the idea, so embedded cache is a library inside your application which runs together with your process. In case of Java, it runs inside the JVM. One problem, if you look at this diagram, the one problem is that imagine that the request comes to our system and it first goes to the application on the top. The business logic is processed, we store the result in the cache, everything is fine. However, the next request may go, the same request may go to the application at the bottom. And then we have to execute the business logic again, because these caches are completely separate. So one idea for how to improve the embedded cache is to use embedded distributed cache. This is still the same architecture. We don't change the architecture. However, we will change the library we use inside our application. So this time we will use Hazelcast as a library. Hazelcast is just a library. It's like Guava, so it's not a framework or anything. You just change the library you use. And this time, each cache will form, in each embedded cache in your application, they will all form one caching cluster. So they share the data. And it is just the library, so if we stick to this example in Spring, all we have to change is the different cache manager, and so that is the whole configuration that you will use Hazelcast instead of the default Java concurrent hash map inside your whole Spring application. So let's see a very quick demo on how we run exactly this configuration in two applications and how the cluster is formed. So in this demo, this is exactly the configuration we've seen on the slide. So we start the same two Spring Boot applications, and you will see in a second that I started them locally on my laptop. So, and you will see in a second that they form one caching cluster. So you see the first one started. This member, it means that is the first cache that started. And the second one joined the first one, and they have one caching cluster together. Now you may ask, like, how is it possible that they automatically discover each other? I run it on my laptop, so when you run it locally, it will use multicast to find other members and form one cluster. However, we provide different discovery plugins for different environments. So if you happen to use Kubernetes, then you use just Kubernetes plugin, and it will internally use Kubernetes API to find other cache members. What we do is we provide the plugins for most common cloud solutions, but if you use something that we don't have a plugin for, you can still use Eureka, which means that you set up your own, or Zookeeper, or it means that you will set up your own service registry like server. And then Hazelcast can use Eureka to discover themselves. We invest a lot in this discovery plugin, so you can read on our blog how to configure Hazelcast for each environment. So that is about embedded cache and embedded distributed cache. Let's look at the pros and cons of embedded cache. So from the good side, it's a very simple configuration deployment because it is just a library in your application. We use Java, but for any programming language, you will find your library for caching. The good thing is also that the latency is very low because it's inside your process, so it's super fast. We cannot do anything better. And you don't need any ops team or ops effort needed because it's managed together with your application. However, from the downsides, the management of such cache is not flexible because if you would like to scale it up, like your cache is full, you would like to have more space, then you have to do it together with your service. It's also limited to JVM or whatever your programming language is, meaning that you cannot run one service written in Ruby, the other in Java, and they will not form one cluster because there is probably no such library. And the downside is also that data is collocated with the application, which may not sound like a problem. However, usually for big enterprises, it is a problem because of the data security. That's why usually if they build a big system, they don't use this pattern. So that was about embedded cache. The next pattern is a different architectural pattern, and it's called client-server. This may look familiar. It's kind of a database style. So you set up a cache server, and then all application connects to the server using cache clients. The flow is the same. Request comes to the load balancer, then it goes to the application, and the application checks in the cache if such request was already called. So if you compare this to the embedded mode we've seen before, just a while ago, there are two main differences. So the first is that this part is separate. It's separate, it means that it needs some separate management. Usually it will be a separate ops team, or it can be, if you follow like the DevOps, it can still be developers who maintain it, but someone has to maintain it, deploy it, write configuration, and so on. The second difference that between this and embedded mode is this part. This part it means that now application uses cache client to connect to the cache server. So if you think about it, like even the cache server can be written in Java, we can use a client library written in Ruby or in Python. And that is very common strategy in case of microservices. That is usually what you do. You have one cache server and a lot of different microservices with a lot of different, written in different programming languages. They all connect to the server. In this architecture, you may also use some other alternatives to Hazelcast, like the most popular in the web world, Redis, or a little old but still use Memcached. These two solutions, Redis and Memcached, you cannot use them embedded because they are written, I think, in C, which will not make possible to embed it in some Java, Kotlin, whatever application you write. So Redis and Memcached, the only possible way is to use client server. How to use client server? If you'd like to start Hazelcast, we have just a simple script. It will start the server for you. So you start one Hazelcast node, you start another, they discover themselves automatically like in embedded mode. If you use Kubernetes, which is now like hot topic and most people are moving to Kubernetes, you can use our Helm chart. Helm chart is a package manager for Kubernetes. With that simple command, it will install a Hazelcast server. You can specify in parameters how many nodes you want. It will install the Hazelcast server. Now, how to use it in the client side? So you use a slightly different configuration, but it's still all you have to change is the cache manager configuration for Spring. You specify use Kubernetes config, and that's all. It will automatically, using this discovery plugin, Kubernetes discovery plugin, it will automatically discover cache server in the Kubernetes cluster. So coming back to our diagram from a moment before. So since cache server part can be managed by a separate team, we can even move it outside of our organization and move it into cloud. So cloud is still like client server. The idea is still the same. However, it can be considered as a separate pattern because it has a lot of differences, mainly because the server part is no longer inside our organization. But the idea is still the same. Application connects to one cluster in the cloud. So we don't have to think about all this management like backup, scaling, security, and so on. Nevertheless, like it's still the same architecture, no problem with distribution if we connect client-server mode. How to configure this? Again, like in Spring, if you use Hazelcast Cloud, there is also, for other, I will speak about Hazelcast Cloud because I'm from Hazelcast, but you have another solution, like if you want to use Redis, you go to Redis Labs. The idea is exactly the same. So for Hazelcast, you provide all you have to provide is discovery token and the password for your cluster, and then it will automatically find your cluster on the web and connect to it. So a quick demo of how to set up the cluster in the Hazelcast Cloud. You can go to this website and then create an account and start your free clusters. So So first we go to this website, and in the UI we select like new cluster, and then we have to specify the cluster name, and what is very important is the cloud provider and region. Why is it important? I will tell you about this in a second. Then you select the cluster type and click create. In a few seconds we should see the metrics and then information that the cluster is created. We already have the metrics. There is nothing in the metrics yet because we didn't add anything to the cluster. If we click on configure client, then you will see the setup for the most common programming languages, and you can grab the discovery token and the password from there. If we go to our Spring application, we have to provide here the discovery token and the password. And then when we run the application, again, it's the same application. I didn't change anything. Like this application actually has nothing. It's just this configuration. And if we run it, in a second, it will connect to our Hazelcast cluster, which is located in the cloud. Our cluster had just one node, one member. This is this cluster. So pros and cons of client-server and cloud solutions. So good thing is that data is separate from the application. It has separate management, which means that if there is some peak in using cache server, we can just scale it up very easily without touching our application. And it's programming language agnostic. So it's well-defined, the protocol between client and server. So you use client library, you can use whatever you want. From the downsides, in case of client server on-premise, you have separate ops effort. And the second downside is something we didn't mention yet, but now the latency becomes a little more difficult. I mentioned you in this demo that it's important that which cloud provider you choose and which region. So the cloud provider and region should be exactly the same as your application, because otherwise you would imagine that you run your application in US and have your cloud server in Germany. Then it will be slow. But it's even more important. Even if you have in the same geographical location, then it's important to have it in the same cloud provider. Meaning, if your infrastructure for your application is AWS, then create a cache cluster in AWS. But it's even more difficult, even more important, because you can still be in the same provider, in the same region, but you can have multiple network hops in between connecting to your cache server. That is why your client server should be in the same network than your application. In case of the cloud version, it should be in the same VPC. So what we do in Hazelcast Cloud, we also provide a way to do a VPC peering between the network where your application is run and the network in which the server is run. Because we are in very strict requirements in terms of latency. It's even more than the database. Cache is something that should be really fast. This is the space of in-memory data computation, where the fact that it's in memory, it must be super, super fast. So that's how we covered the basic pattern. These two first architectural patterns may have sounded obvious to you because embedded and client server are quite old. However, this third pattern, Sidecar pattern, is something completely new. This time this diagram is Kubernetes specific because Sidecar pattern is mostly seen in Kubernetes environment, and actually it's limited to container-based environments. So in Kubernetes, a deployment unit is called a pod. And a pod contains one or more containers, which are always deployed on the same physical machine. So usually a pod contains just one container. However, in some scenarios, you may have additional containers responsible for some additional logic. For example, such additional container can be a logging agent container that will send all the logs from your application to some external logging system. This additional container is in Kubernetes world is called a Sidecar container. So we can do the same and put our cache as a sidecar to our application and deploy it in one Kubernetes pod. So this time the flow looks as follows. Request comes to our system. It goes to the Kubernetes service, which is kind of a load balancer in the Kubernetes environment. Then it goes to one of the Kubernetes pods. And the rest is exactly the same as before. Application gets the request. It connects to the cache server, which happens to be this cache container. It's always located on the local host, so we don't have, because it's the same physical machine, so we don't have any problems with discovery. And all these cache containers in all pods, they all form one cache cluster. So Sidecar can be seen as something in between embedded mode and the client-server mode. It's like embedded because it's the same physical machine. It uses the same resource pool together with the application, and it scales up, down together with the application. Also, we don't need any discovery because it's always available on the local host. However, it's also similar to client-server because we can use different programming language. After all, it just uses cache client to connect. And there is some isolation between app and the cache. How would it look like in the code? So in the code, we would have like client configuration with the static configuration because we know that our cache server is on local host. How would we configure this in Kubernetes? Is we have like deployment configuration with two containers. The first one is our application, so it's business logic. The second one is it's always the same. It's the cache server. Pros and cons of such solution. So good thing is that configuration is again very simple, and we have low latency. It's not in the process, but it's the same local network. And there is some isolation of data and applications. From the downsides, we are limited to container-based environments. You will hear about about this in Kubernetes. The management is not flexible again because it scales up and down together with the application. And technically, the data is collocated in the same application pod, which does not have to, but can be a problem. The next pattern, and the last one, is something completely different. Because so far, it was always the application that decided if a value should be cached or not. This time it will be different. We will put the cache before the application. So the application does not even know about caching. Again, the request comes to our system to the load balancer, but just after the load balancer, you have a cache. So it's cached at the HTTP request level. And then in this yellow box, it's checked if the request was already executed, and we can reply with the cached response, or if there is no cached value, then go to the application. A very mature solution is from NGINX. You can configure it actually together with your load balancer. So if you use NGINX for load balancer, then you can configure caching with such a small part of the code. Obviously, you can include more properties, but the most important one is the path where the cache values are stored and the key zone. So NGINX is a mature solution. You can use it on production, no problem with that. However, it has some problems. Like, first thing is that it's only HTTP based. This is maybe not such a big deal because in microservices, usually it's HTTP based unless you work at Google and use protobuf, or have some very like strict requirements. Then you may use protobuf, but otherwise use HTTP. It's not distributed. It is not highly available, and the data is stored on a disk, which again might not sound like a big problem. However, like it is a big deal in this in-memory data grid area, that you would like to be guaranteed that your data is in memory. What you could do is use a plugin to NGINX. However, the plugin is like, for Hazelcast it does not exist, and for Redis it exists, but it's not much mature at all, so I would not recommend it for production, but this is something you can use. We can think about it like the same pattern, but again complicate it a little bit, and to merge like sidecar pattern and reverse proxy pattern. It's something different, so it could be again like a different architectural pattern. Again, with the sidecar, we limit ourselves to the Kubernetes environment. Now the flow is as follows. Kubernetes service receives the request and passes it to one of the pods. However, this time it's not the application that receives the request, but the reverse proxy cache container. It checks if the request is cached, and if it's not, then it passes it to the application container. So the application does not know that such thing as reverse proxy cache container exists. Application does not know about caching. And this fact has some good sides and bad sides. So maybe let's start from what is good. Let's come back to this diagram from the beginning of this presentation, which is a classic microservice system. So microservices use each other, they have different versions and can be written in different languages and frameworks. Now, if you would like to introduce caching to this system, then you can actually say in a declarative manner, without touching the code of the service, that these two services, I would like them to be cached. And this is very good because you don't risk like breaking some code in a service. You don't have to change anything in the code. It's completely separated. This is how it would look like in the Kubernetes configuration. So again, like this time, we have here actually three containers. The last one is our application, still the same. Then we have caching proxy. So this is this caching proxy you've seen on the diagram. We also need an init container, which will do one thing. Init container is something that runs before actually pod starts. And our init container will change how the networking works in the pod. Because normally it's the application that would receive the request. However, we would like to change it. So this init container will change our IP tables so that the request, any external request with the port, let's say 80, that goes to our system, will go not to the application directly, but first to the reverse proxy, and then reverse proxy connect to the application using the same port, but using loopback. So this is what this init networking container, init networking script will change in our IP tables. If you look at this diagram and how we added the cache, it's kind of a caching injection. It makes you think this diagram about the service mesh and Istio thing, which is like now becoming like the most popular thing in the world. Like 2 days ago, I was on the conference, and the whole conference was about the DevOps conference, but the whole conference, like almost all the talks were about service mesh, Istio. That is what is going on now with the world. And if you go to the Istio page, you have a very similar actually diagram, because the Istio, what it does, it's the same idea. Istio lets you add functionality to your service in a declarative manner. So you don't change anything in your system, but say, I would like to use, like, from the service 2, I would like to control the traffic and send like 90% of the requests to the version 1 of service and 10% to the version 2 without changing any code. So Istio actually could have this caching functionality, but it does not have at the moment, but they plan to support like caching this way. They not only plan, there is, if you go to their like GitHub repo, there is an open PR, so it will become soon a big thing. However, such approach with this reverse proxy caching also has some bad sides. So if you detach like the cache from the application, there is one thing that becomes way more difficult, and that thing is cache invalidation. Actually, if you look anywhere on the internet, what causes the most of the issues with caching, everyone will tell you the same, it's invalidation. Meaning, when to decide that the cached value is already stale, that I should not use the value from cache, but I should go directly to the database. If you change thing in a database, how do you know that the value was changed? So in case of the application, we can do at least something in the application code, in the logic of the service to decide if I would like to invalidate some of the cache values. However, if the cache is a separate thing from the application, and application does not know about it, then we are limited to some HTTP basic stuff like timeouts, e-tags, generally like timeouts. So this is actually a kind of difficulty. Short summary on the reverse proxy and reverse proxy sidecar caching. So the main good thing is that it's configuration based, so you don't need to change anything in your application in order to apply caching. It's also programming language agnostic. It's actually everything agnostic because it does not even touch the code of your application. And it's very consistent with the containers and microservice world. From the downsides, it's difficult. It is difficult to do the cache invalidation, and there is no mature solution yet. So Istio is implementing this. We in Hazelcast did a prototype, a kind of proof of concept, but there is nothing that you could use on the production yet. But it will become. In a year or two, you will hear about it more and more. From the downside, I mentioned also it's a protocol-based, but as I said before, I don't think it's a big deal. If you're using microservices, you already use HTTP. So like this, we came to the end of our agenda for today. So as a very short summary, I know there are a lot of patterns here. So how to structure this in one's mind? I thought about creating a small decision tree, which can help you decide on which pattern to use in your system. So the first question I would ask if I were to design a system is if there is a need for my application to be aware of caching. If no, then do I use container environment or no? If no, I can use just mature solution from NGINX and reverse proxy. If yes, then use reverse proxy sidecar as soon as there is a mature solution yet. My estimate for this is in 1 or 2 years, people will use it. Now, if your application needs to be aware of the caching, then the next question you can ask is, do I have a lot of data on some security restrictions? Basically, is my application kind of big enterprise thing? If no, do I need to be language agnostic or is it containers based? If no, then just use simple embedded. If yes, use sidecar. However, if you work in a big enterprise, big organization, they usually, generally with a big system, then the last question you have to ask yourself, is my deployment, is my infrastructure in the cloud? Do I use AWS, GCP, or Azure for the deployments? If no, use client server on premise. If yes, then use some cloud-based solution like Hazelcast Cloud or Redis Labs or whatever else is on the market. So as the last slide, I've put some resources you can read about caching. So first one is our proof of concept of HTTP reverse proxy Sidecar. The second one is, the first one is a blog post about Sidecar Hazelcast. The second one is this reverse proxy caching prototype, proof of concept. Third one is a very good blog post about caching in general and some caching best practices. And the last one is a very good video presentation on how to use NGINX for reverse proxy caching. And with this last slide, I would like to thank you for attending this talk. So, sorry? Do you have any questions?
Yes, hi. Hello? Hear me? Okay, so can you hear me?
Yes, yes,
okay.
I can hear you, yes.
So you guys made a proof of concept in Hazelcast for reverse proxy Sidecar for Kubernetes, yeah? And you said that the hardest problem is to basically invalidate the cache. And if you keep your application separate, so completely unaware of the caching Sidecar, so how did you guys solve this invalidation problem?
So
thanks.
This is like the main problem that you just cannot solve, in a sense that the whole idea is that application is not aware. That's why you will not solve it. Probably if we were like to create a production-ready solution, there would be a lot of like engineering problems that we just have to tackle. But this, what I mentioned, is about like that this will probably never be solved. The best thing you could do is to create, for example, an endpoint with but then application again becomes aware of the cache, which actually breaks the whole thing. So I would say this pattern is only this pattern dedicated to some use cases where your application does not need to know about caching.
Hey, thanks for the talk. I have a question about the service you mentioned, Istio, I think. Are there any other good sides or features or anything, since I haven't heard of that service, besides the one where you can load balance your request, for example, switching to the new version of API and then doing 10%, 90% and increasing?
Yes. So yeah, Istio is like actually a very hot topic. So really, I recommend it to everyone to play with this. If you don't want to install it yourself, you can even go to the Google Cloud and there's even a tick box to say, create a Kubernetes cluster with already Istio installed. But to answer your question, like, so Istio is basically for, as for now, it has like the feature of traffic management, so exactly what I mentioned. It has a feature for security, that you can have a security also declared like you declare in a declarative way. It make you think about like Asper-oriented programming. So you think about in a service about the business logic, but you don't want to think about the same security thing in each of the service. That's why you can add it to in a declarative way in Istio, so that every request coming is secured. So basically, as for now, the Istio is for network control and security. But they are adding features, like caching is one of the features they will add, definitely.
Any more questions?
Hi, one more question on the cache invalidation. So in a scenario where the application is unaware of the cache, of course it doesn't make sense to forcibly make it aware. Is there a possibility for the cache itself to become aware that certain entries need to be invalidated? For instance, if you're fronting a regular microservice with REST API, making any kind of a put or delete request to a certain path would mean that whatever is caching the entity on that path is no longer to be used. Now, I'm not aware if the caches can do that. Do you have any experience there?
Yeah, to answer your question, like, yes, if the application is not aware, then you can still cache will invalidate entries. You can inside the cache define a strategy how it should be invalidated. Should it be timeout or some eviction policy, like invalidate for me the last used entries. That is still fine. However, like what you mentioned after this, like that you could, basing on the HTTP request, do some invalidation. I think it would be possible. I mean, there's no solution implemented yet, so this is all theory. But I think so. NGINX does not do it. There is no solution yet. But in theory, you could think about something like that. However, like the problem I see is that it could work with super standard REST requests, like. But in any other, like when you have some business logic, then it could become more difficult. So I'm not sure if I would have to think about it if I were to implement it. Because it sounds good. Like if you follow like REST maturity model and you have everything like, then yes, let's do it this way. But I would have to think if there are not too many like corner cases and for things when. So yeah, I don't have like the answer. Like, would it make sense? It's a good idea. Yeah.
Okay, thank you.
Any last questions?
If no questions, then thank you again.